Distant galaxies so far away, captured by the Webb telescope, reveal little specks of light that have been traveling for more than 13 billion years. At the farthest edges of the cosmos, where light has traveled for over 13 billion years to reach us, the James Webb Space Telescope has unveiled a breathtaking panorama of the universe in its infancy. This glimpse into the depths of space isn't merely a marvel of engineering or astronomy, it is a journey backward through time, revealing the universe as it was shortly after the Big Bang. When the telescope turned its mirrors toward the boundaries of the observable universe, it encountered something both unexpected and deeply profound. The James Webb Space Telescope didn't just see light, it saw structure, motion, formation, and mystery. It saw the raw cosmic canvas being painted by forces we are only beginning to comprehend. The revelation came in the form of highly detailed infrared images capturing galaxies so distant their light has been redshifted to the very edge of detectability. These galaxies were not the simple, amorphous blobs scientists had long assumed early galaxies to be. Instead, they were surprisingly well-formed, massive, and complex. The implications were immediate and paradigm-shifting. If such organized structures existed this early in cosmic history, then the current understanding of galaxy formation, which predicted a slower, more chaotic evolution, would need substantial revision. What the James Webb Telescope had uncovered wasn't merely an edge to the observable universe, but a breach in the boundaries of known cosmological theory. One of the most striking discoveries was the presence of what appeared to be mature galaxies forming just 300 to 400 million years after the Big Bang. This timing poses a direct challenge to established models of cosmic evolution. According to standard theory, galaxies should have taken much longer to reach the scale and structure observed in Webb's deep-field images. The telescope's near-infrared capabilities allow it to peer through cosmic dust and detect these early light sources in exquisite detail, revealing spiral arms, starburst regions, and even evidence of active supermassive black holes. These aren't the primitive building blocks that scientists had expected. They are fully realized systems, behaving in ways that suggest the universe may have been more efficient at creating order from chaos than anyone had anticipated. This discovery demands a re-examination of how matter coalesced in the early universe. Dark matter, long theorized to provide the gravitational scaffolding for galaxy formation, might play a more dynamic role than previously assumed. Alternatively, there may be unknown mechanisms at work, perhaps interactions between dark energy and matter, or undiscovered physical laws that govern the high-energy conditions of the infant cosmos. Whatever the case, the James Webb Telescope has pulled back the veil on a period of cosmic history that now looks dramatically different from what textbooks have described for decades. Further revelations came in the form of protogalaxies caught in the act of merging. Webb's observations showed gravitational interactions taking place on a scale and with a clarity never before imagined. The tidal forces, gas inflows, and emergent spiral structures observed in these mergers offered a living laboratory for understanding how galaxies grow through collision and accretion. More than mere snapshots, these were dynamic systems alive with the motion of stars and gas as they swirled together to form larger and more complex galaxies. Observing these interactions so early in the universe's timeline speaks to a hyperactive era of formation, challenging the assumption that the early cosmos was a quiet, diffuse environment. One of the telescope's most intriguing capabilities lies in its spectroscopic instruments, which allow scientists to analyze the composition and temperature of ancient light sources. From the edges of the observable universe, Webb detected chemical fingerprints of heavy elements such as carbon, oxygen, and even iron, elements that can only be produced in the hearts of stars and then scattered by supernovae. Their presence in such ancient galaxies implies that several generations of stars had already lived and died by the time this light began its journey toward Earth. This pushes the timeline of stellar evolution backward and raises questions about how rapidly star formation proceeded in those first 100 million years. What lies at the edge of the observable universe, as revealed by Webb, is not a boundary in the traditional sense but a horizon of perception, a limit to how far back in time we can see. Yet even within that limit, the telescope has exposed a cosmos teeming with activity, filled with surprises that defy our most refined models. It forces a deeper philosophical reflection on the nature of observation itself. Every photon Webb collects from these distant realms is a whisper from a time when the universe was young, dense, and hot, a message encoded in light that has crossed unimaginable gulfs of space and time to tell us how things began. This is not just a scientific breakthrough, it is a redefining moment in the human story. The images from the edge are not only data points, they are portraits of ancient light caught in the act of creation. They show us a universe that formed structure almost as soon as it existed, that harbored the seeds of galaxies, stars, and perhaps even life far earlier than anyone had dared to believe. The implications stretch far beyond astrophysics. They suggest that the fabric of spacetime, the laws of physics, and the dance of energy and matter may be far more interconnected and elegant than previously imagined. Moreover, the James Webb Telescope's revelations about the edge of the observable universe have reignited interest in cosmic inflation theory. The patterns observed in the distribution and shape of early galaxies might encode subtle clues about the inflationary epoch, the fraction of a second after the Big Bang, when the universe expanded faster than the speed of light. If these observations can be tied back to specific inflation models, they may help unlock the mysteries of that primordial moment and explain why the universe has the structure it does today.